Hello, welcome at the second session. Thank you for joining me. Yeah, we have few students in the classroom, it's good, and I can see both of you. Okay, let's finish what we did yesterday, because we did talk about the area under the curve, and that's quite important concept, quite important topic. And I did copy one of the slides from yesterday's session, from section 4.1. And I will do one more time. Do you remember the limit that I don't know for some reason, but I was confused between the difference between the N and I. And I can, of course, as soon as the session was over, I knew it, and I know, but okay, I will change one thing on this slide, and we will do the exercise really quickly, what we did yesterday, and then we will start section 4.2. Okay, that means we remember the main problem was to find the area under the curve, limited by two vertical lines, A and B, and we know the process. B minus A will give me the length of the entire segment, the interval. Delta X is the width of each stripes or of each rectangle, because we will build the rectangles. And this is the thing. We have B minus A, which of course is the length of the entire interval, and we dividing by N. By N, because N could be, I can divide by 4 rectangles, I can divide by 40, 4,000, I don't know, 4 million, of course, big number, huge number, infinity, but N stays N. Yeah, that's what I have to keep N. And then I also have my sample points, like X sub 1, X sub 2, X sub 3, 4, 5, 6, 7, 8, and then N, X sub N minus 1. And these sample points are changing. That means eventually they will become X sub N. That means this formula theoretically should be, let me move this, X sub I. Yes, and we remember A, because we will have A plus 1 times delta X, A plus 2 times delta X, A plus I times delta X. That's we have to keep I. And then I is changing from 1 to N. But delta X is just always N. Because I was kind of like I was confused. That means please remember the sample point. Of course, the right-hand side, we will define A plus I times delta X. 1 times delta X, 2 times delta X, and so on. That means this will stay I. Okay, that means now we remember this. The main problem was, we did the approximation, but the main problem was to find the area under the x squared, parabola x squared, from 0 to 1. We still don't have a nice formulas. We will have the formulas and we will solve it like in, I don't know, in few seconds, okay? But for now, we have the concept, we have a definition. That means I can say that this is my area, and of course, by approximation, or maybe by taking the value from the textbook, I don't know how to say, we know that is 1/3. But let's compute this. That means we know R sub N means that we will be adding, we will be adding the areas of all of the rectangles. And the area of the rectangle is base times the height. Base is delta X, and height is the value of the function at the sample point. And sample points are changing from 1 to N. And of course, we do have infinitely many of those. Okay. Limit as N goes to the infinity. I from 1 to N. And now we remember delta X is simply 1 minus 0 over N, because B minus A, which is 1 over N. 1 over N, and then sample point is a, the first value, plus I times delta x. So please remember, because we will use few times today also. A is of course 0, and I times 1 over n. That's like 1 times 1 over n, 2 times 1 over n, 3 times 4, and so on. That means this will be I times 1 over n, and function is defined as a x squared. That means this is like my x, let's say x sub I squared. Yeah, I can use the colors. I'm not crossing this out. Okay. Yeah, because I like this exercise. I is changing. Okay, as we have I squared and we have n squared. I can possibly remove that blue. Okay, but that's x sub I. And we know why I'm squaring, because our function is the value for, maybe I can write here, for x sub I will be x sub I squared. And I did compute x sub I is I times 1 over n. Yeah, I times delta x. Okay. Maybe one more step. I mean, few more steps. Limit of the sigma from 1 to n. And we do have I squared. N times n squared will be n cubed, and times I squared. And now this formula with respect to sigma, we can see only, like, sigma is only indicating that I is changing. Yeah? Like I is changing from 1 to n. That means everything what is not I will be considered as a constant, and we can put in front of the sigma. That means I will put 1 over n cubed in front of sigma. I keep saying I, because I can tell you, if you will take Math 141, we had lots of sigma, lots of infinite series, and I keep saying n equals to 1 because of the other parts. Okay, and then I squared. That's the reason that okay. And then you remember that was the formula that we could use, because this is the moment, like the addition, because this means that I will be adding the squares of the counting numbers, 1 squared plus 2 squared plus 3 squared. And we do have the formula. That means this is the moment that I can remove, I can get rid of the sigma. And let's see. Do you remember this formula? Was n plus 1, and I think 2n plus 1, all over 6. That's, I didn't copy that slide, but one of the slides from yesterday's session is providing 3 formulas for I squared, and I cubed. Okay, and now we can see that when I distribute everything, because now we have to compute a limit. When I distribute everything on the top, I will have 2n cubed as a leading term, and 6n cubed in the denominator. N cubed, the same degree, 2 over 6, of course, it is 1/3. Yeah, that's what we did. Yeah, we did integrate, I can say this, we did integrate actually function x squared on the interval from 0 to 1. Because today I will like add the new terminology, yeah, which actually that's the integration, finding the area under the curve. And we can see no proper integration formulas, no proper like anti-differentiation formulas, yeah? Just simply using the concept, the definition. Okay, because I like this idea. Later, you will like, oh, somebody will ask you to integrate, and you will have lots of formulas. You will integrate, and sometimes we forgot like the main concept behind the integration. We forgot like what really integration means. And do you remember from yesterday, like the integration, like, did I say something like in really, really broad term, what integration means? Do you remember? Like something like I said that we can, yes, David, that's good. That's good, because you will see like lots of, as soon as, I don't know, maybe you will be in some, and add, that's it, the addition, the sigma, we can see limit of the sigma, adding infinitely many items. That's integration. And if you will be, I don't know, if some, like maybe you will be part of some team, some project, and somebody will say, oh, we have to possibly integrate, you can always think like, oh, that means let's slice it, like whatever problem you will have, I don't know, whatever shape, whatever, to compute the area, to compute the volume, to compute the work, to compute the force. I mean, lots of, wherever the rate of change is given and we have to like recover, but yeah, I will. Then you can always think that you can slice, you can define one item and then add them together. Yeah, that will be the idea. Can you hear it or not? Okay. My son's supposed to watch our dog, but of course. Okay. That's me. Yes, I really like this process. Probably I will not really ask on the test to do this, because always, I did ask many years ago, but some students, they were telling me that it's too difficult. I don't, yeah, okay, let's get here, different ways. Okay, what I have, okay, that means I have this slide. That means as we just used, yeah, we use the limit of the sigma, which means we add infinitely many items, and the items were simply the area of the rectangles. Delta x is the width, excuse me, the delta x is the width, and the height, excuse me, I will just drink my tea. Crazy day. The delta x is the width, and the f of x sub I, the value of the function, is the height. Okay, and so we have expanded form. And now, as I just mentioned, we have lots of, because this is simply this part. Yeah, this part is adding, yes, adding infinitely many items, and this will be always different. Yes, like later, if we will have some applications, the blue part will be different. As I said, could be the volume, could be work, could be center of the mass, could be force, could be length of the curve, could be distance, yeah, the total distance traveled if we have the speed. Different, yes, different things, but always the idea, yeah, will be like add all of them, infinitely many of them. That means, since this is used so widely and it's extremely important, as mentioned before, we do have a special name and special notation. That means we will not always use the limit of the sigma. Okay? That means, let's see. Of course, the special name is an integral, but we will say a definite integral, because we have lots of details. Everything is defined that we will call a definite integral. We will also define later indefinite integral, but for now, a definite integral. Okay, and now let's kind of like match definite integral, and that's, do I have this? Oh yes, I have it. Okay, that means we know the limit of the sum, we know what this means, value of the function, which is the height of the rectangle, delta x is base. And now what's happened? Limit, okay, of the sum of the sigma simply will be replaced with the integral symbol. And the integral symbol is just like, yeah, just S, summation, addition, the long S, yeah, like the elongated S, and was introduced by Leibniz, yeah, and it's just called an integral sign. Okay, and of course means the addition, the summation. And what we will do, we will, again, limit of the sum means the integral. We will integrate a function f of x. That means this is important. Integrating f of x. And what's happened? The delta x was actually like, delta x was the base of this rectangle. That means it had its value, like its amount, the line, the tiny line segment. But for the integral symbol, this will become dx, and dx doesn't really have meaning or like on itself. It's only indicating that we will be integrating, which means we will be slicing the x-axis. Because we can also do everything with respect maybe to y, or maybe with respect to z, like depends, calculus 3 or different. Yeah? But this dx doesn't really have value. It's not like that I'm multiplying. I was multiplying the delta x. The limits from a to b is telling me that I'm integrating, and the whole integration process, it's taking care of this dx. This is just the indication that we integrating with respect to x. Instead of dx, we may have dy, yeah, later, but dx doesn't really have like value, but we always have to indicate integral of the function f of x dx, which means with respect to x. Like we remember derivatives was similar, dy dx. Yeah, like wasn't really, it's just the notation that we integrate differentiating function y with respect to x. Yeah, that means something like this. I will erase this for the not confusing. Okay, we will still have, that means that's actually, yeah, that's this. Let's see. Oh, I do have some explanation. That means the integral symbol, of course, is s. A and b we will call limits of integration, lower limit and the upper limit. The function that we integrating we will call integrand. Similar, like we have the quantity or function expression under the square root, we will call radicand. That means this is integrand. And as I said, dx doesn't really have a meaning on itself, it's just indicating the independent variable, because we will be integrating with respect to x. Okay, that's me. Now officially we can call integration, but we still, theoretically, we still don't know that that's the same process like anti-differentiation. Yeah? We just know this weird limit of the sigma. But yeah, slowly we will get there. Okay, we okay with this? Oh, that's also important. Definite integral, yeah, definite integral, like we did integrate actually. I can say we got 1/3. That means definite integral is a number. Yeah? It's the number. Again, it's something like having computing a derivative at the given point. Yeah? It will be slope, will be a number. Computing the derivative in general, we will create a new function. Yeah? That means similar will be for the integral. As soon as we have limits from a to b, we will have the exact value number. Yeah? Because this theoretically means the area under the curve from a to b. If I remove a and b, I will have a new function. Yeah? It's similar to the, but definite integral means the limits of integration and it's a number. Okay, and a little bit more theoretical, but if you copy the first slide is, yeah, it's not, I just include all of this information. Again, definite integral is defined as a limit, right, of the sum of value of the function and delta x. And we know that star means the sample points, but we will always use the right-hand side. And x sub I, did I type it? I type delta x. I can maybe write that. We have to know how to compute delta x just in case. And we know that is the entire interval divided by n and the sample point. a, the beginning, plus I times delta x. And that's, yeah, remember I, because I don't. Okay. And that's the right-hand side. Right-hand side sample points. Okay. And yeah, that's simply the definition of that box. This formula in the box is the definition of the definite integral. Oh, another information. Always when it's the introduction to the topic is, that means this, okay, that means definition of the integral, okay, includes a summation, like we know, summation of the areas of the rectangle. And this sum was discovered, was like determined by one of the German mathematician, Riemann. Okay, that's the reason that you may sometimes heard, instead of like saying, oh, approximate the area under the curve, like using, I don't know, 10 rectangles, and then we will be dividing the given interval by 10 rectangles, adding together. Instead of saying this, I can say compute the Riemann sum. That means the Riemann sum is simply addition of all of these areas of the rectangles. But we may notice that n probably will be a finite number. As soon as we add a limit, which means n is infinity, we're creating a definition of the integral. That means I can say that the limit, this box, is simply a Riemann sum. That means the limit of the Riemann sum is a definite integral. Yeah, that means Riemann was theoretically playing with the finite number of rectangles. We integrating a function with respect to x. Right? That means the limit of the Riemann sum is simply the integral. Yeah. Okay. That means Riemann sum. Please remember, because you may have a question, compute a Riemann sum. Just simply adding all of the rectangles, nothing else. And I have again some comparison. Ooh, Riemann sum, definite integral. Oh, okay, that we can see. Again, the same thing, Riemann sum and definite integral. It's almost the same, but definite integral, in terms of the geometrical explanation, the area under the curve, we can say it's perfect, because the definite integral includes that infinity. Riemann sum, not necessary. I can have finite number of, but as soon as I add limit, they are both, yeah, they are both equal. Yeah, this means limit of the Riemann sum is a definite integral. Okay. That means if the number of n, if the number of rectangles is finite, we can see it's still approximation. But if it's infinity, it's perfect, because I can perfectly fit the line and compute the areas. Okay, I think that's maybe one more slide and we will start computing. Oh, okay, let's come back. Because of course, I'm using the word limit of the sum, limit of the Riemann sum, and everything what I'm like showing you, I'm drawing, or I'm presenting a function based on the function which is positive. Yeah? Positive function, which means is placed above the x-axis. And everything makes sense, the areas will be positive, because we have to remember one thing. In this definition, or even here, we do see the value of the function, yeah? Which of course, theoretically means it's the height. Yeah? The height, oh, let's say here, doesn't matter. It's the height of the rectangle. And as soon as the function is positive, everything works. The height is positive. And I can call this is the areas under the curve. And that's actually what the definite integral means, the area under the curve. But now, what's happened if my function is placed below the x-axis? What are the values of the function below the x-axis? What will be the value if I will draw a function? I can erase maybe. Of course, thank you, Noah. Like we can see, we have, let's say from here. Now we will have, if part of the function, because I will not always control this, I will always have this ideal situation that, oh, everything is positive. No, 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 I may have a negative function. I should be able to integrate. That means, let's see what we will do. Yeah? We will add one more thing. That means what's happened, yes, if the function, yeah, if f of x is positive and also negative, yeah, at some values in the given interval. And I think I have, okay, I have this. That means let's try to do this. Evaluate the Riemann sum. Yeah, that's actually good exercise. For the function, just a nice linear function, x minus 3, on the interval from 0 to 5. Taking the sample points to be the right endpoints, and n is 5. That means we will divide the entire interval by 5. How can I start? Okay, I didn't type the solution. Okay, I'm just trying to, that's what we will do. We will try to compute, oh, no, okay, let's compute delta x. That means delta x is b minus a over n. Of course, 5 minus, I don't have to even, that means delta x will be simply 1. We will go by 1. I will draw a function, maybe. I typed something, but I don't know if this is. Okay, a function f of x equals to x minus 3 is just the straight line with the slope 1 and y-intercept negative 3. Maybe like that? Oh, do you think that's the right line? Okay. And now I can go by 1. That means I will have 1, 2, 3, 4, and 5. Okay. And I will divide 1, 2, 3, 4, 5. Yeah, that means I'm just, because what Riemann sum means, that means Riemann sum, I can, because right-hand side, we will have actually 5 of them. That means this will be from 1 to 5, delta x, the value of the function. But simply what this means, we can even skip the sigma notation. I have to add the areas of 5 rectangles. Oh, actually, let me expand this. We will compute. That means this means that I have to take the delta x. Let me erase this. Times the value of the function for 1, because we can see 1 is on the right-hand side, and then delta x plus the times the value of the function for 2. Let's factor out delta x, because delta x is the same for everything. Value of the function for 1, value of the function for 2, value of the function for 3, 4, and 5. Okay, that's what I would like to, because we know delta x times the value for 1, delta x times the value for 2. Okay, let's actually build the rectangles. That means 0 and 1. And we remember 0 and 1. 1 is on the right-hand side. That means value for 1, which is actually negative, will give me the height. That means this is my first rectangle. Between 1 and 2, 2 is on the right-hand side, and value of the function for 2 will give me the height. As soon as I got the value, I have to draw horizontal line. Between 2 and 3, 3 is on the right-hand side, but the value for 3 is 0, nothing. Between the sub-interval between 3 and 4, 4 is on the right-hand side. That means the horizontal line at the value 4 will give me the height, and 4 and 5, 5 is, okay. That means the area, the Riemann sum which is the area of all of these rectangles, are the areas of these blue rectangles. But now we can see, because that's my point. Since now I shouldn't even maybe use the word areas, because that common sense will not really let me do it. In all of this definition, Riemann sum, the definite integral, I will repeat one more time, we're using the actual value of the function. That means if the function has a negative value, we will have a negative value. Okay? That means let's find out. What is the value for 1? Can you tell me what's the value for 1? We can just substitute instead of x1, and this is function. -2? Please check my, yes, thank you. Okay, that means this is -2. -2. What about value for 2? Value for 2 will be 2 minus, thank you, -1. -1. This is 1, that means I shouldn't be worried. Okay, value for 3 is actually 0. It could happen, we remember. Value for 4, what's the value for 4? 4 minus 3 is 1, thank you. And value for 5 is 2. Thank you for helping me, because always the arithmetic. Okay. Okay, that means actually what I have. Are we getting 0? +1, +2, -1, -2, because this, yeah, I really would like to indicate we will keep the actual value. That means this is gone, okay, 0. That means the Riemann sum is actually 0. Yeah, good, actually good. Yeah, good. We can make some nice conclusion. That means now what I will say. The Riemann sum, since the Riemann sum is part of the definite integral, the definite integral, we can call not just the area under the curve. We will have a special terminology. We will call net area. If it's below the x-axis, it's negative. If it's above the x-axis, it's positive. Right? That's how we can distinguish the difference. That means if you will integrate later something and you will realize, oh, my answer is negative, it could be negative, then you can think, oh, probably most of the function or even the entire function is negative, is placed below the x-axis. And what 0 is telling us? What do you think in terms of that net areas? 0 means that I think it's balanced. We have exactly the same amount of the region above and below. Yes, that's. I always like to ask. I don't have. Okay, I have the other screen. Okay, that means this. Yeah, it could be 0, could be negative. That means please, because sometimes the students will say, oh, it's actually always positive. No, could be negative. And I think, yeah, I just type this, but we just said, oh, everything what will be below, it's negative. Everything what is above is positive. Okay, that's what we did. The Riemann sum is simply 0. Okay, and I have, of course, the summary page for the net area. Yeah, we will call the net area. And since the definite integral represents the net area, like we can find out the areas like above the x-axis, which I will say a sub 1 and a sub 1, and whatever is below, we will simply subtract. Yeah? I mean, we will find the value, but the value will be negative. Yeah, that's mean everything what is above, and we will call net area. Okay, that's mean a quick exercise, really quick. Okay, that means I can draw something, and the only thing that I want you to tell me, if the net area, of course, net area means the area under the curve or like bounded by the curve. If the net area is positive or negative, that means when, let's say my function will be defined like that, from A to B. And the definite integral represents this part. Of course, this will be positive. Yeah. And now if I will draw something like that, from A No, not like that, not like that. You probably know. Let's say like that. From A to B. Definite integral, this will be negative, okay? And you can probably guess. Let's actually draw we know this function. It will be 0. That means let's look at this really nicely. Integral between 0 and 2 pi of sine of x with respect to x, it is 0. We don't need any formulas, of course. And I'm sure later, even maybe on the final test, if I will ask you this question, you will not say 0 right away. You will really follow all of the formulas, all of the arithmetic, and we can all the values from the unit circle, which we can make always some mistakes. Yeah. And finally, hopefully you will get 0, but we can please always remember about the areas. Yeah? It's not easy, I know, because you will be focusing on calculation, but it's always here. Can we get the answer, the definite integral of the sine function between 0 and pi? This one we need more tools, yeah? We don't know. It's positive, yeah, it's definitely, yeah, it's definitely positive, but we don't know. Okay, but definitely from 0 to 2 pi. Okay, that means we know the net areas. Okay, let's do this one, because now I have a few questions. That's actually, I think I copy from, yes, from one of the final tests. Estimate the area under the graph x squared on the interval between -2 and 0 using 4 equal subintervals and the right endpoints as a sample point. Okay, that means interesting. Yeah, I didn't use the same question I can ask, find the Riemann sum. Yeah, not just. Okay, that's what we will do. Function x squared, oh, from negative. That means maybe I can move my okay, this is x squared. And from negative to 0. And n is 4. Can you tell me what delta x will be? Because that's my interval from -2 to 0. And I have to divide by 4. That means it will be half. I can still use my formula for some. That means b is 0 minus -2. Of course, we have 2 units between -2 and 0, and divide by 4. It is half. Okay, that means we will go -1, -½ and -3/2. Okay. And simply we have to find out the areas of the rectangle. That means now the right hand side. Between -2 and -3/2, this is on the right hand side. That means this dot, this level will give me the height. -3/2 and -1. -1 is on the right hand side, and this will give me the height. -½ is on the right hand side, and actually 0 is on the right hand side, which 0 will give me 0. Okay. This means we have right hand side, 4 of them, and I can maybe list them. Delta x times the value of the function for 3/2 plus delta x times the value of the function for -1, delta x times the value of the function for -2, and delta x times the value of the function for 0. It's just 4, that means I don't really have to. If this will be 40, I will use the sigma notation. Okay, and delta x is 1/2. Please remember, I can factor out, but please remember, because it's not always 1. Okay, and function is just x squared. That's mean negative 3/2 squared, negative 1 squared, negative half squared, and 0 squared. And we can see everything is positive. That's we don't have problem with some confusion, because we might be confused at the beginning. Oh, arithmetic. I'm counting on you. This will be 9/4. This will be just 1, but I can put 4/4. This will be 1/4, great, and 0. Okay, that's we have 9 plus 4 plus 1, 14. Over 4, yes, and times half. It is, I'm so happy that 14/4, which actually is 7/2, which is not on the, 14/8, which I can say 7/4. That's what I was, yes, and we do have that option. Because sometimes it's the only common mistake, of course, if we really understand the concept, is sometimes forget about delta x. Okay, that means you know how to estimate this. Of course, it's, did we overestimate the area or underestimate it? Definitely under. Yeah, we can see the blue rectangles. We still have this white, white gaps. Yeah. Okay, let's see what else we can have. Oh yeah, you will. And the final test will involve these questions. Okay, let's see what else. That's the same, because do we have time? Okay, let's do, because I have, okay, shall we do it? Because it's the same question. Involves a little bit negative. No, let's skip it. Let's, maybe, because I have another one, which okay, if we will have time at the end, we will come back. Let's do this. Okay, thank you for, because it's the same idea. I will draw a function, I will have an interval from 0 to 2. How many sub-intervals? 4. Yeah, we will divide actually the same thing, but we on the positive part. Yeah, the same idea. Let's leave it. Okay, that's mean now we we remember for the derivatives. Some of the function, especially when we had like some sharp corners or discontinuity, derivative was not defined. Because of course, like sharp corners, I can't really draw a tangent line. No tangent, no slope, no derivatives. The same thing is for integration. Not all of the functions will be, how do you say, integrable. We will not integrate, okay? But what we have, of course, we can't accept, we can have some sharp corners, that's not a problem. We can't accept like infinite discontinuity. Let's see, that means I have just, if function is continuous function, okay, or this is always surprising, we can have finite number of jump discontinuity, because as soon as like let's say we have function defined here and maybe here, I don't know, something like that. Yeah? That we can see, we can have maybe C, maybe D from A to B. That means even if function has like discontinuity, yeah, I can still find the area. Yeah, this is not a problem. The problem is if we have like the infinite, like an asymptote. No, yeah, then some like infinities involved. But when we have jump, the finite number of jump discontinuity, we can still integrate. That means, of course, we always saved when we have continuous function, but even jump discontinuities are also good. We can definitely integrate. Probably we have to integrate maybe 3 times because we have some situation at C and D, but we can definitely integrate. However, also I can tell you, even if we have asymptote, we will call like improper integrals, we can still do something, but that's calculus 2. Okay, but for now we will say that we only need continuity function or jump discontinuities. Okay, now what I have, I still have this definition. Okay, that's this is probably, but probably you saw this multiple times tonight. That's the definition. Definite integral means like we're replacing limit, and the sigma function is the function, dx replaced with delta x. Delta x is defined like that, and sample point is defined like that. Because now, how can I make sure that you understand this? I might ask you I will not ask you to do the process that I did, the 1/3 that we got the area. I will not ask you. That's, even if it's nice and beautiful process, I will not ask you to do this. But I would like to ask you to rewrite, having a limit of the Riemann sum, yeah, to rewrite as a definite integral, or definite integral rewrite as a limit of the sum. Only this. That's me. Let's see. I can ask you this, yeah, that page, reference page. Remember, important. Okay. For example, this one. Set up an expression for the integral as a limit of the sum. Okay, which means I can say rewrite this integral. Integral is from 2 to 5 x to the power of 4 dx. Rewrite this integral as a limit of the sum, limit of the Riemann sum. That's what we have from 2 to 5 x to the power of 4 delta dx. The integral sign is a limit of the sigma from 1 to n and goes to the infinity. And then function, okay, and delta x. Of course, function that we integrating f of x is defined as a x to the power of 4. And then f of x sub I can say x sub I to the power of 4. But to be like, to provide more details, I have to provide a formula for my x sub I. And we remember is a plus I times delta x. This means the final answer that you will probably see one of the options. I have the multiple choice somewhere. Okay, that means we have to put what is f of x sub I, and we have to compute delta x. Who can tell me what is delta x? Can you tell me what will be delta x using this information? What is the length of the interval that we integrating? Delta x, yeah, it is 3, and we will divide by n because we have to divide by n. N could be any number, but of course in this case it's infinity. That means delta x is 3. Everybody's okay where the 3 come from? Just the number of units, yes, thank you. Number of units between 2 and 5. Shall I do this? 5 minus 2. I did the other way. Okay, and now, and we remember x sub I is defined as a plus I times delta x. Yeah, that's the formula. Okay, a, the beginning of the interval is 2, I, and delta x is 3 over n. That means that's what I can, and function is defined as a x to the power of 4, and my x is 2 plus 3i over n. Okay, and I think I can leave the answer like that. I do have all of the details. That means this blue box represents that definite integral. We can see we have, it is 3 over infinity, but we can see n is infinity. Yeah, we do have this indication. That's here. That means I will not put 3 over infinity, but yeah, it is. We're dividing 3 by the length, the entire length, we're dividing by n. N is, yeah, infinitely many of these rectangles, yeah? Approaching not infinity. No, it's approaching infinity. N is approaching infinity. I don't know if I understand, but yeah, n is approaching infinity, and the entire delta x, if we have the quantity 3 over infinity, a constant over infinity, of course is tiny, yeah, almost 0. Number over infinity is a small number, because we know infinitely many of these rectangles will give me 0. But no, this is, yeah, n definitely goes to the infinity. Okay, and I think I have, oh, I did type the solution. John, did I answer your question? Oh, because I don't want to, everything we have to, okay. Oh no, why no? No, because I want you to make sure, okay, this is the formula, right? And delta x is always the entire interval that we're integrating, and we will divide by n. But I can't use like infinity. Infinity is just a symbol. That means always the limit holds that information. Yeah, I don't know. You can put the mic on and you can ask the question if you tired of typing. No, we have to make sure that we understand. You said yes and no. Tell me what no means.
Can you hear me?
Can I hear you? Oh, you can type.
Well, I do have my mic on. Can you hear it though? Okay, so I'm just asking, is n actually infinity, or is it just approaching infinity?
Oh, you're really specific. Yes and no. I mean both. Oh no, I think we can say it's approaching infinity. N is approaching infinity. That's more. I will say n is infinity, but that's not a proper mathematically, because what is infinity? We don't know what is infinity. Infinity plus infinity is still infinity. Infinity time, yeah. That's oh no. N is approaching infinity. Okay. Yeah, that means it's not, we can't say it's exactly infinity, because infinity doesn't really exist as a one like finite number. Okay, that's me. You would like to be no good, yes, yeah. N is approaching infinity. Good. Okay, good. Okay, good. Okay, let's see what else I will ask you. But no, good. I like when you asking questions. Oh. Let's see this one. It's almost the same what we did. Express the definite integral from 1 to 4 of x cubed dx as a limit of the Riemann sums, taking the sample points to be the right endpoints. We will always use the right. Okay, that means the same thing, but I managed to type all of the sigmas. Okay, that means what we have. We do have x cubed dx. And we know that the integral sign means the limit of the sigma, of the Riemann sum. N is approaching infinity from 1 to n. And function at the sample point and delta x. Okay. Of course, we know that function is x cubed. Function at the sample point will be xi cubed. And that means we will have a limit, or maybe you know the answer. Function is x cubed, and delta x. Can you compute for me delta x? What is delta x? The entire length dividing by n, which is, yes, between 4 and 1, we have 3 units. Yeah, again, that means 3 over n. Okay. And we will have x sub I. And who can tell me the formula for x sub I? The x sub I is a plus I times delta x. And what is A? What is the beginning, the initial point of our interval? It's 1 plus I times 3 over n. That means I can put the final answer, limit (3 over n), but this will be A plus I times delta x. Okay, that means this is, okay. Do we have that form even? It is C, not D. Oh, so similar. Yeah, please confirm that is C. Definitely not A and B, because A and B, the option A and B is showing me that the A is 0. Like, can you see 0 plus, and A is not 0. That means I think C, because it's 3 and 3, 3, 4, 4, 3, yeah? Okay, that means that's the way that I will ask you. That we can see the integral symbol will be replaced with this. Okay, and then it's just the function, and dx delta x, they match.